Okay, let's talk about mole fractions. Now, mole fractions is just, again, the amount of something, of material, in that portion of it, okay, by mole. So this, if we had weight fraction, right, we would know by weight the methanol and then the water, and then we would know that the total has to always equal 1, okay? So we look at mole fraction in the vapor and then the mole fraction in the liquid, since we're looking at a distillation column. And it's key that both of these fractions, again, are, there's a certain portion of the vapor in the liquid and a certain portion of the liquid in the vapor. As we know, they all always must equal 1, okay? Now, an immiscible mixture of methanol and water, if the mole fraction of the water in the vapor form is 0.4 and its mole fraction in the liquid is 0.8, what is the mole fraction of the methanol in this vapor form? So let's look at it. So we're going to go to this table, okay? So we have the materials, and then we have the mole fractions in the vapor, and then the mole fractions in the liquid. We're given that we have the mole fraction of water in the vapor is 0.4, and we're given that the mole fraction of the liquid of water is 0.8. So we can calculate YA, because we know, again, everything must equal 1. And we're looking here at a binary mixture. This is generally the case for binary mixture. However many are in there, they would have to give you so many of them in order for you to determine the mole fractions, okay, if you were using more than one, a mixture of more than 2 binary mixtures, more of 2, okay, more than 2. So let's look at the answer here. So if it's 0.4 in the mole fraction in the vapor, 0.6 is the methanol. Okay, now we're going to ask the next question is we want to determine XA. So that's what this next one is. So again, we look at our table. All right, we know that the mole fraction of the water in the liquid form is 0.8, so we know that the total has to equal 1, so we know that XA has to equal 0.2. Okay, that's just, these are going to be questions on the test, but they're straightforward and they're not very difficult. We're only looking at binary mixtures. Now let's calculate relative volatility. We use these numbers in order to determine it, okay? So the relative volatility is they always take the mole fraction of the higher, more volatile substance, okay, on the top of the vapor, and then the bottom is the mole fraction of the less volatile in the vapor, and then over here, the mole fraction of, again, the less volatile and this liquid form here, and then the more volatile here. So let's put those numbers in, okay? So we see these numbers here are 0.6 and 0.4, respectively methanol, water, and then 0.2 and 0.8. So let's put them in. So we look at these numbers. So our more volatile is this YA is the more volatile substance. So we know it's 0.6, okay, from the previous table, and then 0.2. So that would be in the denominator, okay? So here it's 0.6 and here it's in the denominator. And then we know these two just have to equal 1 and these two have to equal 1. So 0.8 and 0.2 equal 1, so we know we have the numbers in the correct spots. So the number is 6. And what we find that the relative volatility really indicates how well the separation is. Numbers of 6 or higher mean that you'll have a really good clean separation, and most of the vapor will be what you're looking for on the low boiler, almost 100%. And then in the higher boilers, with the bottoms will be the other substance, almost 100%. Okay, so again, distillation. So more accurately, right, it's the separation of more volatile materials from less volatile. And then you do partial vaporization and condensation as it's going up the column. So you can do batch or continuous, simple, single stage, fractional, multi-stage, vacuum here, but we're not going to do flash distillation or azeotropic in this talk. Okay, let's go on. So batch distillation. So in the batch distillation, you just have one pot and you fill it completely with whatever it is that you want to separate out. Okay, and then you're left with, you're boiling it. You boil that, and then the most volatile comes off the top, and then what's left at the bottom is the bottoms that are the lower boilers. Okay, now what's important to understand when you're doing batch distillation is that these changes, okay, that are occurring are always happening all the time. So your composition of your material, okay, is changing. Because why? You're not adding any more to it. You're just boiling off what you have. So if you start with a 50-50 of methanol and water, as you boil it, right, the methanol is coming out of that 50%, out of the 50-50. So that 50% starts to get higher and higher up here to 70%. So it's leaving this pot that was 50-50. So now that's 25%, and now 75% of that whole composition is now the water, okay? The vapors are constantly changing because, again, the composition's here, and then the overhead distillate, and they're occurring continuously because you're batch distillation. And the reason is, again, no replenishment of the feed material. Now, if you look here again, you're just looking at this. This is what we talked about. We do one whole, we just load this kettle full of material, and then we just boil it off, and the highs, the low boilers, the light composition comes here, and then the heavies come down here, okay? And that's just generally how it's done. Now, what will happen is you can have a series of these done together, right? Series of these batches to get purer and purer, because you can only do so much in one batch. But this ends up being what we end up seeing as this fractional distillation, or a whole large column that you do continuous distillation, and then you get finer and finer and purer off the top, okay? That's just all this is showing here. Okay, so some of the equipment, you have a vapor line, you have an evaporator, you have a condenser, 2 tanks here, an overhead distillate receiver, and a still pot, and then a feed line. And you may also heat that, you may not, because batch distillation, you just generally boil it to where you need it to be, and then a vacuum system to keep the flow of the column going the right way as well. So here it is right here. You just dump in some of the material. This is your heater, okay? It could just be steam. And your A, which is more volatile, comes off the top, and you condense it and cool it, and you get purified A, and at the bottom is your B's. Okay, so that's just what we said here. So you're just heating 2 substances, and then we're just going to say A has the higher boiling point. I'm sorry, the lower boiling point, higher volatility. Okay, and then it's just the concentration changes, right, as it's going along here. A starts coming out here, so A and B now becomes less A and more B. Okay, and that's just what this is saying here. So it's just that as A is boiling off, you're just losing more of it from that whole pot. Okay, so when A is distilled off, the boiling liquid in the pot is just mostly B. Okay, then you find out if you're done and you can't take any more off that you needed to, because you just don't have the heat capacity, or they form an azeotrope and they will not separate anymore, then you shut down and then you start a new batch. Now, vacuum batch distillation. It's important to understand that there are some compounds that have a very high boiling point. When this happens, you can get thermal decomposition. So it'll break down and or form some other products, and then you're ruining the purity and the quality of what it is that you just wanted to make. So when you run a column and you have a high boiling point, you may want to use vacuum distillation. Why is vacuum? And why might a high boiler benefit from vacuum distillation? Well, that's because you are able to you have a pressure that's lower, and then we know when we have a lower pressure, our boiling point is dropped. So therefore, you can boil this at a much lower temperature and then not run into this thermal decomposition. So once your pressure is lower, then you can just start again, and you do the same thing as the batch distillation. You just are running under a different pressure, much lower, and vacuum, and then you're running at much lower temperatures, therefore. And then you just run the batch distillation just as we just said previously. Now, fractional distillation is the one that you see generally in the refineries. So you're taking off fractions from the pot. So if you have crude oil, right, you have a ton of stuff in crude oil, and they're all boiling at different places in different temperatures. So you're going to be pulling things off at different places. So again, you can have continuous fractionating column. Okay, you'll have a stripping section where these are all the plates below the feed plate. Okay, in the reboiler area. Rectifying are all the plates above the feed. Okay, and then the plate, or the feed plate tray, is called the feed plate tray, and that's usually at the point where it's entering the feed material. Usually this is heated, and it's at the temperature of mostly where the feed material's boiling point is. That's where you want to put that feed in there. Okay, so this is just a picture here. So your feed, as you can see, comes somewhere in this column at a temperature. This column runs based on differential pressures, higher all the way to lower. Okay, the lower boilers come off the top, and they're reflux. They're sent off to the reflux column, that some are pulled off for product, some are fed back to the column. And then you have your reboiler constantly reboiling here and keeping this hot and then feeding it there. And sometimes you take off the bottoms as well. Okay, you'll have a distillation column, an evaporator, a condenser, a reflux drum, a still pot, a feed line, and then trays or packing. Sometimes you also write trays and or packing. So here you can just see one of those different types of column: rising vapor and falling liquid contactor. These are really huge. Partial vaporization and condensation occur on each tray. Sometimes you can have these kinds of trays. These are called bubble cap trays. Okay, we'll talk a little bit more about these in the next the next presentation next week. You can have the reboiler. Okay, this is just basically a reboiler or evaporator at the bottom, and it's constantly heating up this column so that you get the vapors coming up the top and then the liquid at the bottom. The high boilers stay at the bottom. Then your condenser takes all of the vapors off the top. Okay, passes it through the heat exchanger, which in this particular instance is a cooler, and then you have the liquid distillate comes out and goes into a reflux drum. This reflux drum here then collects it, and you can always reflux it back through the column. Okay, so you can either send it right back to the column in total reflux, and you may just do that for certain reasons. It's not usually done though because you're trying to make a product. You could pull off all of the product, or you can do both. And generally, in order for a column to operate at most highest efficiency, you do both of these. And then the reflux again. Part of it is pumped back through the column, and some of it is taken off to collect as a product. This does improve the purity of the top stream as well. Okay, now this is a really important factor. You will have to know this for your test. A key operating parameter to control the concentration of the less volatile component is its reflux ratio. And it's basically a simple calculation. The reflux ratio is the liquid returned to the column, usually in gallons per minute, divided by the overhead distillate product taken off, usually in gallons per minute. And they call that an L/D ratio. Okay, so let's do a problem on that. Sorry about that. Okay, if the flow of the final overhead distillate returned to the top of the column is 6,000 moles per hour, or it could be gallons per minute, just what doesn't really matter, just as long as they're in the same units. And the flow rate of the distillate product taken off is 1,000 moles per hour. What's the reflux ratio? So you take the liquid returned to the column, which is this 6,000, and you divide it by the amount of that is pulled off as product, which is 1,000. So this ratio is 6 to 1. Okay, and you'll hear that. That'll be definitely on your test. Now the bottoms. The still pot is located at the bottom of the tower where the heavy component is collected and pumped to the bottom storage tank. Okay, so that just takes that off. And then the preheater, again, is an interesting, important piece that it does. You heat the feed as it's entering the column. Then there's trays and packing. Trays or packing are located in the tower, and they're just different types of internals, and we'll go into more detail in the next week's unit. So there's just different. This is a really nice one because it just shows you there's a vapor distributor. There's some fractionating trays here, maybe a chimney collector tray, support grid for more packing. Okay, and then another bit of different type of packing. So there's a sieve tray, a bubble cap tray, and a valve tray. The sieve tray has little holes, just like as if you have a colander for your water when you're doing pasta. So the water drains out the hole, and then on the top would be the vapor passes through. A bubble cap, it has to push up through these caps, and the bubbles and the vapors push through the bubbles. Through the cap, pushes up the cap, and then goes through the liquid and comes out the top. And then this is just a valve tray, another type. This is structured packing. Now let me just see again. Here's just a different example of what it looks like. Okay, you could just have like the packing here, and then distributor, liquid distributor to make sure that it's evenly distributed. And then here are the different types of packings that you can have. Okay, so let's just explain a comparison of tray versus packed. All right, so if you have a large column, you would want to use the tray. A small column, you might want to use packed. If you have continuous, it's tray. Batch would be packed. And then complexity, high for a tray, and the low for the packed. And then efficiency, again, all these are high, and they cost more. And then low on this side. And then this is cleaning is harder for the tray. Packing's easier. A lot of times you just dump them and then repack them. Okay. So some principal requirements for tower packing. It must be chemically inert to the liquids of the tower. It must be strong, not excessively heavy, and must contain adequate passage for the streams. And it must provide good contact between liquid and vapor and reasonable in cost. Okay, so I just wanted to show you again another diagram of this. And you can look at that. This is the stripping section, and this is the rectifying section. Okay, and so this is the column. Okay, so just review your notes for review the notes in class and then these PowerPoints. If you have any questions, please let me know. Thank you very much. You have a good night.